Okay. Good afternoon, good evening, good morning, everyone. First of all, I would like to welcome everyone to the 62nd section of the PD, the Applied Mathematics Seminar. Today we have a great honor to receive two brilliant mathematicians, Professor Xavier Ros Oton and Professor Maria Jesus Esteban. Both will be presented by Professor Enrique Fernandez Cara. So please, Enrique.
Okay, thank you very much. Good afternoon, good evening to everybody. I'm going to present with pleasure Xavier Ros Oton, that is a research professor at the University of Barcelona in Spain. He has previously worked at Zurich and also at the University of Texas in Austin, and his field of work has been mainly the regularity of partial differential equations, in particular in the context of free boundary problems. He's nowadays very well known because he has contributed with very interesting and recent results to these fields. And the proof of this is that he has received several prizes. Recently, he has been awarded with the Stampakia Gold Medal in 2021, for example. And I have to say also that he has worked with very celebrated people also, like Alessio Figali and Luis Caffarelli. So we have the pleasure to have him among us, and I thank him deeply for his acceptation to participate in this seminar. The title of his talk is going to be the singular set in the Stefan problem. So when you want, you can start your talk. Please share your document again and come on.
Great. Well, thank you very much for the invitation, and thank you very much also for the kind presentation. I will present more or less a recent work that is a joint work with Alessio Figali and Joaquim Serra, and it concerns the singular set in the Stefan problem. Okay, so let me start by describing a bit what is the Stefan problem. Then I will go into what can we say about the singular set, or what do we mean by the singular set, and then I will present the results. Okay, so the Stefan problem is a free boundary problem, and essentially it's the most classical free boundary problem. It describes the melting of ice. Okay, so this was introduced almost 200 years ago. And we can think about a picture like this one. So we have say a container, and then inside this container, that could be full space maybe, or can be a bounded domain or anything. Inside this container, we have a system which is that we have liquid and solid water. Okay, we have some initial conditions. Let's say at the beginning, it could be that everything is ice, or that already half of it is ice and half water, or whatever. And then we want to understand how this system evolves with time. Okay, and then as time goes by, what will happen is that this ice will melt. Okay, so we want to describe the melting of ice. This ice will melt, and then this will create this creates an interface that is moving with time. Okay, and this is what we call the free boundary. So the free boundary is this interface between solid and liquid regions, which move with time, and is a priori is an unknown, is a part of the unknown of the problem. Okay, so this is a PDE problem in which we have an unknown which is more geometric, say. Okay, and then here we would have some boundary and some initial conditions everywhere. Okay, but the important thing, if I look at it as a local problem, I have a PDE here inside. Then what is the PDE? This is the first question. Okay, what is the Stefan problem more precisely? Well, in the simplest case, I will assume from now on that the ice is at 0 degrees. So the temperature here at the ice is 0 exactly. And the water is at positive temperature, strictly positive. Okay, so this is the so-called one-phase Stefan problem, because I'm assuming that the ice can only melt. This is why I'm assuming 0 here, positive here. Okay, and then in the positive region, in the liquid region, this water region, we have so this is the region which is part of the unknown. We have the heat equation. Okay, so the heat equation, if theta denotes the temperature, theta solves the heat equation in the liquid in the liquid region. Okay, but then this set, as I said, is unknown. Okay, so this equation is very well understood. The problem is that this is a nonlinear equation because this set is unknown. Okay, and then we need to complement. We need to add another condition in order to know how does this set evolve with time. And the way that this set evolves with time is the following. So the free boundary is determined by the so-called Stefan condition. Okay, so what is this Stefan condition? The Stefan condition says that on the free boundary, so on this interface, exactly on the interface between liquid and solid, we have this. And this is saying essentially that the velocity, so the speed at which the ice melts, so the velocity of this interface is proportional to the gradient of the temperature in space. Okay, so the speed is theta t divided by the gradient, the modulus of gradient. So this is equivalent to speed equal to gradient modulus of the gradient without the square. Okay, so essentially you can think about dimension 1. You could have like a 0, a part in which this is solid and this is liquid, and then the velocity is exactly proportional to the gradient of the temperature at that point. Okay, so the more gradient you have on the free boundary, the faster the ice will melt. Okay, and this is the physical, and this is like the simplest PDE model for a phase transition. Okay, and this is the so-called Stefan problem. Now, what can we do in order to understand this system? What can we, I mean, of course, our goal is to understand, to have a theory of existence, uniqueness, and also some regularity, some nice properties of this interface. Okay, so the final goal would be to understand if this interface is nice, if it behaves in a nice way, and this equation is satisfied in a strong sense. Okay, but for this, we need some tools. And then an important tool that was introduced in the 60s and 70s, this was the so-called Duvaux transformation. Also, Baiocchi did it first in the elliptic case, a similar one, and then Duvaux did it in the parabolic case, in the Stefan problem. And the nice property that they found was that if I take the integral in time of the temperature, okay, locally you fix near a free boundary point, and I take the integral in time of the temperature, then this problem, I mean, this new function satisfies a new problem, okay, which is that this function is non-negative, okay, just by definition. It's monotone in time, just by definition, because theta was non-negative. And in addition, these two conditions become one. Okay, so these two conditions, that was a condition inside the domain and a condition on the free boundary, just become one equation, which is nonlinear, and is that the heat operator equals a characteristic function with a minus. Okay, so heat operator equal minus the characteristic function of the liquid region. Okay, so now this is the equation that we will study, because this is equivalent to the Stefan problem. If you are away from the initial conditions and away from the boundary conditions, this is exactly equivalent. So this is a local transformation that allows you to understand locally in the interior of the domain. It allows you to understand the free boundary completely. Okay, so it's an equivalence, and from now on, I will study this equation. Okay, so this equation, so the equation that I just presented you, is actually the so-called parabolic obstacle problem. Okay, so its stationary version for this function u is the so-called obstacle problem, and this is why it's called like this, because this is a classical constraint minimization problem in the calculus of variations, which is that you take the Dirichlet energy, okay, and then given a infinity function that is fixed, let's say you fix this infinity function, which is the obstacle, you just minimize the Dirichlet energy among all functions that are above the given obstacle. Okay, so this should be a v, not a u. So this is the function v, which is the one that minimizes the Dirichlet energy among all functions above the obstacle with some given fixed boundary conditions. Okay, this is the obstacle problem. It's one of the simplest constraint minimization problems in the calculus of variations. and then you take v minus phi. As I said, this should be v, and then I take v minus phi, this difference, this height function, and it solves this. It solves that this function u is non-negative everywhere, okay, just by definition, and moreover, its Laplacian is a characteristic function of the positivity region. Okay, this is something you can check, for example, when phi has constant Laplacian. Okay, say that phi is a paraboloid in the simplest case, then you get this problem. Okay, so what we get is a picture like this. So if you look at it from above, what we see is that either u is 0 or u is positive, and we have a PDE. And this is the free boundary. Okay, so this is exactly the stationary version of what we had before. Right? So, and there are two ways to write this. So if I write it with the characteristic function, right, I have that u is non-negative, the heat operator equal to a characteristic function with a minus, and that's it. This is the equation. This can be equivalently written in a different way, which is that, okay, my function is non-negative. Okay, also the heat operator equals to -1 in this positivity region. So I have a linear PDE in this positivity region. But in addition, this characteristic function is encoding something else, which is that the heat operator is bounded globally, okay, even across the free boundary. And this implies that solutions, for example, are C1 alpha in space. So in particular, the gradient in space is 0 on the free boundary. So not only u is 0 on the free boundary, but also gradient u is 0 on the free boundary. So another way to look at this problem is to think that, well, you have two unknowns. One is the solution, and the other is the domain, this u equals 0, this contact set. Okay, these are the two unknowns. And instead of this free boundary problem is actually an overdetermined problem, because on the free boundary, I have that u is 0 and the gradient is 0. So we have both Dirichlet and Neumann conditions. Okay, so we have a linear PDE with both Dirichlet and Neumann conditions. So this is kind of an overdetermined PDE problem. Okay, so this is just an alternative way to look at the same problem. Everything is equivalent, and we can look at it this way or this way. Okay, so let me present, before going into the math, and let me present one more motivation, which is completely independent for why do we care about the Stefan problem. Okay, so the Stefan problem actually appears as well in a completely different setting, which is in probability, and more precisely in the optimal stopping problem. Okay, so if you have a Brownian motion in the full space in a Ren, and you have a given payoff function phi, and then we play the following game, which is that you follow this Brownian motion, and then at any time before a certain deadline, capital T, at any time you can decide to stop. Okay, you say, okay, now you stop, the Brownian motion stops, and I get the payoff corresponding to the point where the Brownian motion was. Okay, and then the natural question is, okay, I want to maximize the payoff. So as a player, my goal is to maximize this payoff that I get. And then the question is, well, should I stop if I'm at point X and time T, or should I continue and hope for better expected payoff? Okay, and when I say maximize the payoff, of course, I mean maximize the expected payoff, because this is something, this is a random process, and I have to take the expectation. So to solve this problem, what people in probability do is to define the value function, which is the maximum expected payoff that I can get for all possible stopping times tau. And then this function v, actually, if you take v minus phi, again, it turns out that it solves a parabolic obstacle problem. So it solves the Stefan problem in a Ren. Okay, so this probability game or stochastic control problem also gives rise to the same PDE, which is what we call the Stefan problem, which is the melting of ice. Okay, and then what we call ice in the Stefan problem, here it's called the exercise region, because it's what you should exercise your region if you think about mathematical finance. Okay, these models are used very widely in mathematical finance, and a typical example for this is the pricing of American options. Okay, so we have two completely different examples for where the Stefan problem appears, and actually there is a wide list of problems in which this Stefan problem or the obstacle problem arise. Okay, so there are classical problems in potential theory, this probability theory in optimal stopping and finance. Then also an original motivation for the obstacle problem was fluid filtration, Then there are, of course, the phase transitions that I described. In fluid mechanics, when you have the Healy-Shaw flow between thin parallel plates. And then also more recent models that are that include these three, which are works by Silvia Serfati or José Antonio Carrillo and others. That, for example, when you study electrons, very large number of electrons that are confining potential, then you are led to a minimization problem for a probability density. And then this probability density is supported in a set, which is actually the contact set in the obstacle problem as well. Okay, so, and then similar models arise in interacting particle systems in biology, random matrices, etc. Okay, so all these examples give rise to the Stefan problem, or in some cases to the stationary version, which is the obstacle problem. Okay, so these are the reasons why do we care so much and why this problem is important for us. Okay, so that being said, what are the main mathematical questions that we have here? Well, the most important and challenging question is to determine if we can prove something about the free boundary. If we can say that this interface that evolves with time, if we can say that it has some nice geometric or regularity properties. Okay, so like simplifying, is the free boundary smooth? Yes or no, right? Or in what sense it is smooth, or to what extent it is smooth. Okay, so this is the main question that we have. And the first results in this direction were established in the 60s and 70s, in which people proved that solutions U are C11 in space and C1 in time. Okay, and this is optimal. So the Laplacian is discontinuous, so you can easily prove that the solutions are not C2, but they are actually C11. And then with a bit more work, you can prove that solutions are actually C1 in time and not better. Okay, and then this still does not answer anything about the free boundary, because the free boundary is just the boundary of the zero set of this solution. So the boundary of the zero set of C11 function could be anything, right? So this still gives you nothing about the regularity of the free boundary. And the first results in this direction were established by Kinderlehrer and Nirenberg in 1977, in 1978, in a sequence of two papers, in which they proved that if you assume, so under the assumption that the free boundary is locally a C1 manifold, then this is actually C-infinity. So if you assume that this interface between solid and liquid, the ice and water, this interface is C1 near a point, then it is actually C-infinity in space and time. Okay, so this is in the spirit of Schauder estimates, for example, in many nonlinear PDEs, which is that once you have some initial regularity, then you can get full smoothness by a bootstrap argument. Okay, so C1 implies C2 and C2 implies C3 just by using results for linear equations. Here, this is much more delicate because it's a free boundary problem, but the idea is the same, is that you use results for linear equations with variable coefficients in order to bootstrap and get these results. Okay, and the real nonlinear question comes now to say, well, but I don't know a priori if the free boundary is C1 or not, right? So in many nonlinear PDEs, what happens is that the most difficult step is like the first one, is to get to this initial regularity. Okay, and then the same happens here. And the breakthrough came the same year, 1977, when Caffarelli proved, this is a famous paper in ACTA, in which he proved that the free boundary in the Stefan problem is actually C1, and therefore C-infinity, possibly outside a certain set of singular points. Okay, so what Caffarelli proved is actually a dichotomy. It's like either this happens or this happens. And the dichotomy, more precisely, is like either the free boundary is C-infinity in a neighborhood, okay, and then in a neighborhood, so given one point, either the free boundary is C-infinity in a neighborhood in space and time, so everything is infinity around it, or at this point, what we have is that the ice has zero density in the measured theoretic sense, in the sense that, for example, you pick this point, if this was ice and this was water, at this point, the ice, when you zoom in, it has zero density. So you don't see, it has zero measure in the limit as a proportion in small balls, right? So this is the dichotomy of Caffarelli. Either you have kind of a cusp that is being created, or everything is infinity in a neighborhood in space and time. So this is a very powerful result that completely separates between regular and singular points. Okay, and the singular ones can only be of cusp type, of zero density. So let's look at the proof of this result, because it will be useful in order to understand later what happens at singular points and what can we say about singular points. Okay, so notice that at this point, we are separating. So what Caffarelli does in his theorem is to separate between regular and singular points and characterize singular points. It still tells us nothing about the singular set. What can we say about singular points? Okay, but this comes later. So to study the free boundary, one considers blowups. Okay, so this is a strategy that comes from minimal surfaces. The idea comes from the theory of minimal surfaces and the works of De Giorgi and many others, and is to consider to rescale your solution. Okay, so you rescale U, rescaling by a parameter R in space. Then to keep the equation, you have to rescale by R squared in time and divide by R squared. Okay, to keep the characteristic function with constant 1. So this is the only rescaling that keeps the equation. And now you'd like to take R going to 0. So you're kind of zooming in both space and time, zooming in your solution and taking the limit and hope for the best and hope that you get some information in the limit. Okay, and then in this procedure, what you need to do is to use, well, first by C11 regularity, this is uniformly bounded in C11, so you can take a limit. And then you need to prove that this limit is non-trivial, is non-zero. And this is a non-degeneracy property of the solution. And then you can, once you have this, you can prove that this limit actually is a global solution to the same PD, is a global solution to the same equation. Okay. And then the key difficulty in all these arguments is to classify blowups. Okay, so you want to do, the idea is that you zoom in, you do this blowup procedure, you take the limit, and then you get more information by doing this. So you get to classify blowups. And this is the crucial point in the theory. And this is what Caffarelli did by proving first that the blowup is independent of time. Okay, so the blowup actually does not depend on t. And second, the blowup is convex in space, which is a lot of information. Okay, so you end up with a stationary solution to the obstacle problem, which is convex in space. And then using this, he could classify the blowups. Okay, and then the blowups are actually also homogeneous of degree 2. So you get a solution which is stationary, it's convex, and it's homogeneous of degree 2. And then using all this, you can then classify and say, well, only two things can happen here. Okay, and the two things that can happen are the following: either this is your blowup, or this is your blowup. Okay, and I forgot the 1/2 multiplying, but it's not important. So there is 1/2 here, 1/2 here. But this is either this is what your blowup, or this is or any paraboloid, any quadratic polynomial could be your blowup. Okay, an example would be this one as a quadratic polynomial. Okay, now this is what you expect at regular points. If you are at a regular point in which, say, the free boundary was C1, then you expect that when you zoom in and take the limit, you get half space full of ice, half space of liquid water. Right? This is what you expect when the domain is nice and there is a separation into two halves. Instead, when you are at a singular point, what you expect is to see that the density goes to 0. So in the limit, you see no ice. So here the ice will be only this line, for example, right? So the ice, remember, is the 0 set. So the 0 set here is a half space. Here is just a line, or could be a point, for example, if you get another quadratic polynomial. And this is actually what Caffarelli proves, that what you expect at regular points is this, what you expect at singular points is this. Well, this is actually the only things that you can get. Either you get this solution or you get this solution. Okay, and this is actually the definition of regular or singular point. And now once you have this characterization of regular and singular points, the last step that you need for the result of Caffarelli is to say, well, now I want to transfer and say that if this was my blowup, right, then I want to transfer the information to my solution U and to prove that the free boundary is C1 near regular points. Right, and this is what he did in like kind of the second part of the paper is this. So after you classify blowups, what you want to prove is that your solution is actually very close, in some sense, to this blowup, and that the free boundary is actually C1. And this is not easy. This is part of Caffarelli's theory for regular points. Okay, so this is the classical theory of Caffarelli for regular points, and now we turn our attention into the case of singular points, right? Because now, remember I said there is a dichotomy. So either everything is infinity at near a point, or this point is singular. But I never said, because it was not known, what can we say about singular points, about the size of the singular set, for example, right? So this is a classical and central problem in geometric analysis in many PDE problems, which is, well, if my solution can have singularities, how large can this set of singularities be? How large can this singular set be? Okay, and in this example, the singular set was just 1 point, so this is one singular point. But actually, there were examples already in the 70s, even before the result of Caffarelli, in which, for example, in the stationary case, there were examples suggesting that you could have infinitely many cusps, one next to each other, and the singular set could be like a one-dimensional Cantor set of dimension, a subset of a line. You can be essentially any closed set, which is a subset of a line, could be a singular set. Okay, and then in time, if you have the time variable, then you expect this to happen maybe for one time. This could happen. Okay, so there are these kind of examples just to have in mind. And then what are the results in the positive direction? The best results in the positive direction that we have? Well, so there were Caffarelli in 98, then Monod in 2000, and Blanchet in 2006, and some others. And they proved, essentially, just simplifying a bit, they proved that in space, so if you take, for example, solutions to the Stefan problem, and you look at the singular set in space, singular points are contained in an n-1 dimensional manifold, which is C1. Okay, so this matches exactly with what I was saying about being any closed subset of a line into D. Well, this is a general statement saying singular points are always contained in an n-1 dimensional manifold, which is C1 in dimension n, when you are in dimension n. Okay, and how is this result proved? Well, this result is proved by saying, well, the blow up is a quadratic polynomial. Then I actually, if I prove the uniqueness of the blow up, which it does not depend on the subsequence, I can actually get that my solution U polynomial plus a small error. Okay, and this small error is in the parabolic distance, which is x squared and t. So it needs to have the parabolic scaling. Okay, and then once you prove this, it follows from Whitney extension theorem that this result holds, that for every fixed time, for example, the singular set is contained in an n-1 dimensional C1 manifold. Okay, and then in the stationary setting, there have been several improvements of this result. First by Weiss in 99, then Colombos, Polaur, Valichkov 2017, Figali and Serra in 2017, and Figali, myself, and Serra also have space in 2020. Okay, so there are several results that improve this in the stationary case only. Okay, and the idea was to improve this. So in the stationary case, of course, this is not here. And then the idea was to improve this too here, this error. The idea is that if you make this error smaller, then you improve this manifold to, instead of C1, you can make it C1 alpha, C2, or even better. Okay, but this does not improve the n-1. Okay, so these results here, they do not improve this. I mean, the n-1 is optimal for a fixed time, so you cannot improve this. Okay, and then in the parabolic setting, we still have one question, which is, it was completely open, which is, well, what can we say about the size of the singular set as a subset of space-time? Okay, what I said now is that maybe there could be one time in which the singular set is n-1 dimension, right? It can have dimension n-1, and this happens. Okay, but what about the size of the singular set as a subset of space-time, right? And so this is what I said. And remember, the free boundary, if you look at it as a subset of a Ren, then is the free boundary, the interface is n-1 dimensional. So this result, these examples are quite bad because they say that the singular set is as large as the regular one for one fixed time. Okay, and then what I would like to have is a result in space and time for which the free boundary is dimension n, and then I expect the singular set to be smaller than n dimensional. Okay, this is essentially the goal for this question, to say that the singular set is small in some sense, and this was not known. Okay, and then such manifold, if you try to prove something in time, you get a manifold which is C1 half in time, which is not good, and actually also it does not behave well with Hausdorff dimension, this C1 half. So it was not even known if the singular set was n-1 dimensional in space and time. Okay, so this is really the first question that was completely open in this setting for many years, and this is the question that we wanted to tackle. Okay, and actually the most natural way to measure this is in the parabolic Hausdorff dimension. Okay, so you don't need to know what is the parabolic Hausdorff dimension. It's just the Hausdorff dimension associated to this parabolic distance, and the Hausdorff dimension is just the natural way in order to measure the dimension of a set in a ring. Okay, so this is our work with Alessio Figali and Joaquim Serra, and then this is the first result that we established, which is the size of the singular set. So if you have any non-stationary solution to the Stefan problem, okay, and I call sigma the full set of singular points, then the parabolic Hausdorff dimension of the singular set is at most n-1. Okay, so now remember, this is optimal even for one time. There could be one time for which this is already the singular set already has this dimension. What we are saying is that when we add all times, it's still the dimension n-1. So this is very good. We like it because this makes the singular set be kind of small. Okay, and then to prove this, we need a much finer understanding of singular points that we established in the same paper. And also, an interesting thing here is that this is the parabolic Hausdorff dimension. So this is actually a bit stronger than it looks, because the time axis has parabolic dimension 2, just because of the parabolic scaling. Okay, and then if you apply this result in 2D, in R2, this implies that for almost every time, there are no singular points at all. So the free boundary is infinity for almost every time. Okay, if you pick a random, you take a solution to the Stefan problem and you just let it flow. This means that if you choose a random time, then you will see no singular points for that random time. Okay, so the number of times for which things can go wrong is, well, it has measure 0. This is what this says, in 2D, of course. Okay, so this is just an immediate consequence of our result. And now, well, it would be very natural, it would be really nice, actually, if we could have the same result in 3D, right? Because 3D is really the physical dimension for which we have the physical model, the Stefan problem of melting ice. And then a very natural question that arises here is, well, can you prove the same result, the regularity for almost every time? Can you prove it in 3 dimensions, in the physical space? And this turns out to be much more difficult than this. Okay, so this is actually somehow the first part of our paper, the first third of our paper, let's say, and then the 2/3 of the paper is to prove this more general result, which is that if we are in R3, and you have any non-stationary solution to the Stefan problem in R3, then for almost every time, the free boundary is infinity with no singular points. Okay, so again, you can think about this as just take any solution to the Stefan problem, let time go by, and then if you pick a random time, okay, so if you pick a random time, then with probability 1, the free boundary will be infinity for that fixed time. Okay, and then in a neighborhood, for every point, there will be a neighborhood in which this is infinity. So all points are regular, and there are no singular points. Okay, and moreover, we can even quantify this a bit more. So with this result, we can say that if I define S as the set of singular times, okay, and by singular time, I mean any time for which there is at least one singular point, okay? So then the set of singular times has the parabolic, has Hausdorff dimension as a subset of R, has Hausdorff dimension at most 1/2. So this is much stronger than saying measure 0 as a subset of the time variable. Okay, so this is much stronger than saying measure 0. We are quantifying the Hausdorff dimension and is at most 1/2. And as I said, this is much more difficult than the previous result. Okay, and a natural question here is, well, is the 1/2 sharp? Well, I don't know, and we have no idea actually, but we will see in many aspects of the proof that this 1/2 is somehow critical. Okay, so if one is to improve this 1/2, we are very sure that you need really new ideas. Okay, so this is somehow we can find examples in which there are infinitely many singular times, but they are countable. So countably many singular times, it's easy to construct. More than that, we don't know. Okay, so there is still the big question, if you want that, if you can improve this. But anyway, for almost every time, this is infinity. Okay, and actually, so this result, notice that this result does not imply the previous one that I wrote. Okay, so this result is specific for R3 and specific for the set of singular times, while the previous one was in all dimensions and was giving you the dimension of the singular set. So both of them follow actually from this more general result, which is the main point of the paper, which is the following. If you have any non-stationary solution to the Stefan problem, and sigma is the set of singular points, then there is a set that I call here sigma star. Okay, so essentially I split the singular set into two pieces. One is sigma star, which is really good, as I will see in a second, and the other is just small, is of dimension n-2, so even smaller than before. So the singular set can be split into two pieces, one very small one, which is n-2 dimensional, and the other which is very good. Very good in which sense? Well, in the sense that it's contained in a countable union of C-infinity manifolds. So now it's not C1 manifolds, but C-infinity. And moreover, these manifolds are C-infinity flat in time, which means that what we can prove for this sigma star is that in every dimension, the projection of sigma star onto the time axis has dimension 0. So on every dimension, you don't see this sigma star for almost every time. So for almost every time, the sigma star does not happen really. Okay, and in a very strong way. Instead, for example, in dimensions 3, the main restriction to this 1/2, to this dimension 1/2 of the singular times comes from here, from the small set. So in a sense, we understand completely the singular set so that we can truncate it into two pieces, a very good one for which we can say a lot of things, and a smaller one, which is of dimension n-2. Okay, and then the bad singular set behaves as if it was of dimension n-2 for regularity purposes in some sense. Okay, and this is the result that we prove, which implies both results that I presented before. And actually, this is what we need to do to refine the understanding of singular points, which is what we do in this paper. Okay. Okay, so what do I mean by improving substantially the understanding of singular points? Well, we need a result that says that at most singular points, okay, so at these points in sigma star, I have a very good understanding, understanding of the solution nearby. Okay, and what I want actually is kind of a C-infinity expansion, an expansion of order C-infinity, of order infinity, of the solution around this point. And this is what we do. Okay, and the expansion looks a bit complicated, but this is what it is. So there exists this set sigma star, such that this is the good part of the singular set somehow, the part that we can understand better. The other part is just n-2, as I said before. And then in sigma star, in this set sigma star, we have an expansion like this, that U equals to this. Okay, I will comment in a second about this, plus a small error that can be as small as you want, because K can be any number, any positive number going to infinity. Okay, you can choose K equal 1,000, and then you have that U is equal to this up to order 1,000. Okay, and then what does this expansion tell me? Okay, well, let's put K equals 2, which is what we had before, right? Before I said that at singular points, I have an expansion for U of order 2 up to a small O of x squared, if you remember. Okay, and this expansion was just a quadratic polynomial. Well, if I put K equals 2, this term disappears, this term disappears, this term disappears, this term disappears, because they are of order of higher order, actually, because this goes squared. So all these terms disappear, all these terms disappear. I only get x dot e here, x dot e here. Here I have the positive part, here I have the negative part, so they just go together, and this is x dot e squared. That's it. This is a quadratic polynomial. Okay, a very simple quadratic polynomial. X dot e squared. And this is what happens when k equals 2. This is the starting point of our result, that u equals x dot e squared up to a small error of quadratic error. Okay, and then what we are proving is that actually, if you want a higher order expansion of order 1000, what you do is you have two separated terms. Okay, one with the positive part, one with the negative part, and they look like two separate fronts. So they look like two separate. The ice is kind of so the liquid region is kind of has two separate fronts. The interface, the free boundary, has two separate fronts that are going towards each other, and they collapse at time 0. This is what happens at this point in sigma star. Okay, these fronts have velocity v plus and velocity v minus, and these q's are just polynomials that satisfy some compatibility conditions. But the important is you forget about this q plus and q minus. This is really for t negative. Okay, this expansion is valid for t negative. For t negative, this is a positive in some region, then there is a 0 region in the middle, and then there is this positive in another region, which is different. Okay, and then, well, this is what we have. This is the expansion that we have, and this gives us a much deeper geometric understanding of most singularities. So we have two velocities of two fronts that are strictly positive, and they collapse at time 0. And moreover, the terms q plus and minus are polynomials that they correspond to curvature terms somehow. Okay, so we have a very visual and geometric understanding of the singular points of sigma star. Okay, and remember, this happens only at points in sigma star, not at every singular point. And this is actually sharp. Okay, and even the dimension n minus 2 of the set sigma minus sigma star is sharp. Okay, so this cannot be improved. So there is a set in which all this happens, and there is another set that could be of dimension n minus 2, in which this is completely false, and the solution looks completely different. Okay, so our results are in some sense sharp in many aspects, and to prove it, we really need a variety of new ideas. So the paper is quite long, and we combine several ideas from geometric measure theory, so from minimal surfaces or similar problems, then many PD estimates with dimension reduction arguments, and also some new monotonicity formulas for this problem, which is nice. Okay, and more precisely, so this is the kind of the toolbox that we have. Okay, and more precisely, what we do is the following. So we start from the expansion of order 2. Okay, so remember, the known expansion was up to order 2. And then by using the results that I mentioned from the stationary case, we can use their ideas, or well, our ideas from the stationary case, in order to improve from the expansion of order 2 to an expansion of order 2 plus alpha for some small alpha. Okay, and then once you are 2 plus alpha, you go and say, okay, what about if I can get to higher order? And then you can do this by using the arguments or the tools from the elliptic setting, which are actually quite more difficult to implement here, but they are roughly the same arguments. And you go from order 2 to order 3, but no more. Okay, so if you take push to the limit the ideas from the elliptic setting, you go from order 2 to order 3 in the expansion, and you are stuck there. Okay, and then the monotonicity formulas, the algorithm frequency formula that we use in the elliptic setting, everything completely fails. You cannot go on. Okay, so with these dimension reduction arguments coming from the elliptic setting and from geometric measure theory, we are stuck at order 3. Then, once we are stuck at order 3, we need a completely different proof to pass from order 3 to order 3 plus epsilon. This is really the key and the crucial part of the paper. This is actually more than 1/3 of the paper, to go just from order 3 to 3 plus epsilon. Okay, and then this requires like a lot of new ideas, because we kind of end up doing a dimension reduction argument, okay, but without any monotonicity formula that is useful. So we need a dimension reduction argument which is very specific and very tailored to the Stefan problem somehow. Okay, and not a more general and abstract dimension reduction argument from geometric measure theory. And then once you are at order 3 plus epsilon, what you see is that you have won somehow, because the expansion up to order 3 plus epsilon, the expansion that I presented before, if you write it for order 3 plus epsilon, you already see that you have kind of two fronts, and they are kind of separated, and they don't talk too much to each other. So then you expect the solution, once you are at order 3 plus epsilon, you expect the solution to behave as two regular fronts, one coming from each side, that they will collapse, but they don't know somehow. So they behave as if they were regular points moving in one way and regular points moving to the other way. And so once you are at order 3 plus epsilon, we can find a new proof of infinity regularity that of course applies to regular points, but more importantly applies to this setting. And we get from 3 plus epsilon to infinity. Okay, and this is one final step which is completely independent, and you get the infinity expansion. Okay, and then once you get this infinity expansion, then you are essentially done, because now with more or less standard arguments, we can prove the parabolic Hausdorff dimension of the singular set. We can prove the projection onto the time axis. We can prove everything that I said. Okay, so this is really the main part of the paper, which is to prove this improved understanding of singular points from which all the rest follow. Okay, and just before finishing, let me go back to 2D, to the 2D case, and then let's see what can we say about the 2D case in this, using this more general result. Well, if you apply this general result into the case, remember that the small part was dimension n-2. Okay, so n-2, when we are in the plane in 2D, it turns out that we get dimension 0. Okay, so in 2D, you can set the Stefan problem in 2D, the set of singular times has Hausdorff dimension 0, which is almost there in saying that the singular set is countable. The set of singular times, sorry, is countable. Okay, so the 0 is of course sharp because it's 0. And then remember that here, even the fact that regularity holds for almost every time is new. Okay, and we are proving much more. Not only the set of singular times has measure 0, but actually has Hausdorff dimension 0, which is way better. Okay, and for this result, the expansion up to order infinity is essential, and thanks to this, we get this result, which I think is nice. And this is all I wanted to present. So thank you very much for your attention. And
I was asking for someone, there is a question to ask. Have you any question? Okay, I have a couple of questions. The first one is regarding the last result you have presented, specific of dimension 2. My question is, if you consider a three-dimensional case with some kind of symmetry, you can get the same result. I mean, for example, cylindrical problems.
That's a very good question. I didn't think about that. So if you consider, I think it should be possible. I mean, we didn't do it, and I think it should be possible. That would be a nice, but it's not obvious. So it does not follow immediately from our result, because if you're in a cylindrical situation, so essentially the points in sigma star, so the points satisfying this expansion, this is incompatible with some symmetries, right? If you have some spherical symmetries, some cylindrical symmetries, say, this cannot happen. So all points should be here. All points should be of dimension n-2. And then it should be a matter of seeing if with the additional symmetry assumption in R3, you can get better than just saying n-2. If you can get with the additional symmetry assumption, see if you can get something better about some better understanding of the singular set. This might be possible. We didn't think about that, so that's very interesting. Thank you.
In the same line, I would like to know if you have considered the problem in which there is a solid boundary limiting the, because you are considering the Stefan problem in Rn, in fact. So, what can you say something with some kind of techniques in the case in which you are limiting the growth of the ice, for example, on one side?
What do you mean? So our result is if you solve the Stefan problem in a cylinder, then you solve. I mean, this result holds, right? I didn't understand. Okay, so and then everything is very specific of this equation. So our problem is that often when you modify slightly the Stefan problem, for example, even if you want to consider the two-phase Stefan problem in which the ice can be negative, I don't know if this is answering your question or not, but if you modify a bit the problem, then probably this transformation is not useful at all, and you don't get this equation. And then if you don't get this equation, then we can do nothing. Even the dichotomy of Caffarelli is not known, for example, for the two-phase. For the two-phase Stefan problem, which is what happens essentially, even for the one-phase, but working in these equations, with these equations, then this is not known. So everything relies very strongly on the fact that we have this transformation, and that then the one-phase Stefan problem is equivalent to this equation. And then this equation has a very nice structure for which we have some monotonicity formulas and some nice properties that we can do, but not these ones.
Oh, okay, but yes, this I can understand. But my question was, in fact, that, for example, in the one-dimensional case, if you impose to zeta and so also to u to be 0 for x equal to minus L, and you try to solve the problem for x greater than minus L, can you apply the same kind of techniques in order to deduce the regularity of the boundary?
Okay, yes. So for example, in general, if we have some boundary conditions, like in this picture, that could be in dimension 1, as you said, with 0 outside, or could be any boundary conditions in any dimension, then our result applies inside the domain, strictly inside, not up to the boundary. But yeah, so essentially, if you are away from the initial condition, you let some initial time pass after the initial condition, and you are away from the boundary condition, then our result is completely local, in the sense that if you solve this PDE in a certain ball for some time, then our result applies. Yeah, it's completely local in this sense. So it applies if you have Dirichlet or Neumann or whatever conditions, because we don't see the boundary conditions somehow.
Okay, thank you. And the last thing that I don't know if this question is interesting or not, but the last thing is the following. My question is, have you any way to introduce right-hand side or something like this to control the regularity of the boundary?
So the regularity of the boundary, you mean the free boundary? Or
yeah, I mean, is there any way to act? Is there any way to act on the equation in order to get regularity? Or regularity is as it is, and you can do nothing for the problem? Yeah,
I think I mean, this is very kind of, it's what it is. I mean, the Stefan problem, it's what it is, in the sense that this equation with this one. So, but I guess you could introduce, if you think of from the probability motivation, for example, from the optimal stopping, what the natural way to put the right-hand side is here you put an f of x multiplying the characteristic function. And then what you can do is that if f of x, what I assume, but we didn't do it, is that if you put the right-hand side f of x here and it's infinity, then the same result should apply, but we didn't do that. So I assume that the same result should apply for any f of x infinity.
Okay.
But that's I mean, that would complicate our arguments. So we didn't do that.
Okay. Thank you very much.
Thank you for the question.
Any other question or? Okay, thank you. I'm going to thank you again for your participation and for your nice talk, and thank you very much.
Thank you.